So, hello everyone. So, welcome to our this week Rogers in Phitchaya seminar. And today we are very glad to call machine learning compiler research and Mangpo. She's currently a staff research scientist at Google DeepMind, and she leads the machine learning for machine learning compilers effort, and her research interests include compilers, machine learning for systems, program synthesis, and sustainable computing. And Mangpo received an undergrad degree from the MIT and a PhD from the UC Berkeley. And she was a recipient of the Microsoft Research PhD Fellowship and the Qualcomm Innovation Fellowship. So now let's welcome Mangpo to give us this talk.
Okay, yeah, thank you so much for the introduction. By the way, I'm not really sure if my internet connection is good or not. So if I froze, please let me know. I think I might have option to do the wire, but yeah, just interrupt me.
Okay, no
And
problem.
yeah, feel free to interrupt me at any point in time when you have questions. And yeah, today I will be talking about the work that I've been doing at Google since I joined almost like five years ago on machine learning for machine learning compilers at Google. And if you look at the machine learning compiler stack at Google, this is also similar to other places, but with some components swapped in and out, right? So at the top level, we have high-level framework that people write or develop their models in. For example, TensorFlow, PyTorch, and JAX. Underneath this framework, what it does is that it translates the program into tensor computational graph, which is then compiled by a compiler to an executable program that can run on various backends, including CPU, GPU, and at Google, we have TPU, which stands for Tensor Processing Unit, that is widely used to run all sort of machine learning workloads. And at Google, we use XLA, which is in the middle, as you can see, which is the compiler that can translate from the tensor computation graph into executable. And today we are going to focus on how can we make the compiler, in particular the XLA compiler, more efficient. And we are focusing on the TPU backend because this is the most widely used backend that we use for machine learning workloads at Google. So the goal of our work is to figure out if there's a way to automatically select optimal compiler configurations at scale for all of the machine learning workloads in our fleet, right? So if you look at the compiler, it is a very complex system, right? The job of the compiler is to transform program written in the high-level language to low-level representation that can be run on various different hardware. And as part of this transformation, it performs optimizations through various and heuristics, right? So want it to be like the developer should be able to easily, quickly test their program. So when they run the compiler, usually it's fairly quick. But then there's a lot of very complex optimizations problem that the compiler have to solve. So what the compiler usually resort to heuristic, which is usually linear or polynomial time to solve that very complex problems. Now, this means that sometimes this heuristic might not give you the optimal solution for that specific program, right? Now, there's a concept of auto-tuning, which is I do not invent. It's been a while for a long time. The idea is that instead of just use the compiler as is with these various heuristics, can we build a tool which is called the auto-tuner to aid the compiler to find a better optimization decisions, right? So you can frame each of the optimization decision as a search problem. And the auto-tuner will search in the space of all possible configuration for that particular program, and it try to find the best configuration according to some performance metrics. For example, the end-to-end runtime of the program, or peak memory consumption, or energy used by the program, right? So this is what we do. We built the XLA TPU auto-tuner that can tune and find the best solution for some of the optimizations that happen inside the XLA compiler. In particular, I highlight some of those optimizations in blue that we have support auto-tuning for. This includes some of the optimizations at the graph level, This include layout assignment, essentially for all the tensor in your graph. How can we lay out that tensor in the physical memory, right? Whether it's row major or column major for 2D matrix, but then for higher level dimension, it's more complex because you have to consider the permutation of all the dimensions. Operator fusion, what is the best way to fuse some of the operation together in order to minimize memory traffic, but at the same time, not incurring some other overheads, right? We also tune decisions like what is the tiling structure, what is the tile size at the kernel level. I'm gonna go into each of these in a bit more detail in the later slide. Now, so the whole idea of auto-tuning is that, okay, we frame these problems as a search, and then once we do search, we also need to be able to evaluate how good the candidate is. And this is where the evaluator, which is the bottom part of the slide. So one most simplest way to do this is to pick the candidates, compile and run the candidate on the hardware, and then measure the runtime if runtime is the objective that we want to optimize for. So you can keep doing this until you exhaust the space, find the optimal solution. Obviously, some of the optimization search space can be extremely large. So you can see that the search process might take a long time, right? So in this work, we also explore ways to accelerate the search process. And this is where the yellow box comes in. This is where we try to use machine learning to reduce the search time. One way is to say, instead of evaluating the candidate by compiling and running on the hardware, what if we have a model that can predict the runtime accurately? If we do, then we don't have to compile and run on the real hardware, and this can, significantly reduce the evaluation time. The other angle we are looking at is also, can we, instead of just using it for evaluation, can we use machine learning to essentially guide the search, steer it towards the more promising part of the search space, right? And I will go into more details in some of these components later. So let's first take a look at how we phrase some of the optimizations as search problems. So for the first one, let's take a look at operator fusion. And here is a very toy example of tensor computation graphs. So on the left, we have computation graph that there is no fusion. So each node is an independent tensor operation, right? And the goal of the operator fusion is to fuse some of these nodes together. And what it means by when you fuse some of these together, it means that, for example, here you can see that on the right-hand side, we have operation add fused with reshape. So when add fused with reshape, it means that the intermediate output between add and reshape, that we don't have to save that into the main memory, right? So we reduce this access to main memory, which could reduce the end-to-end operation time. So when add produce an output, reshape can consume that immediately, right? So fusion can help reduce this memory traffic, but it also have a downside. In this picture, you can see that when we fuse add to all of its consumer, which is reshape and copy, adds get recomputed, right? So on the right-hand side, you can see that add appears twice, one for reshape and one for copy. So doing too much fusion also incur overhead because you have to do recomputation. So it is a non-trivial optimization on how to balance between reducing memory traffic, but it may incur this overhead of recomputation, right? And in our search formulation, we say that we're gonna assign a fusion control bit to each of the node. So here we annotate the fusion control bit in blue for each node, where 1 means let's fuse that node with all of its consumer, and 0 mean do not fuse that node with its consumer. So in this particular configuration, annotated in blue, we will get the graph on the right-hand side as the result, right? So then you can then essentially in the search, you can just mutate or alternating the decision between like 0 and 1 for each of the node and find what is the optimal solution. as you can see that the search space is essentially 2 to the number of nodes in the graph. So if the graph is small, you can potentially exhaustively search everything. But if the graph is larger, then you would not be able to do that. But we will go back into what kind of search algorithm we can do in some of these optimization. Next, let's take a look at another optimization, layout assignment. The goal of the layout assignment is to assign physical layout to all of the tensor in the graph, including the intermediate tensor between the nodes, right? And here I annotate each node with the physical layout for its input and output, right? In this particular example, you can see that the annotation between add and convolution, these are the physical layout for output of add and input of convolution. Now, in this particular example, it have a conflicting layout assignment. By the way, the annotation is basically the permutation of dimension, right? So in this edge between add and convolution, if the assignment is conflicting, what we need to do is to insert a copy, or you can think of it as transpose, to transpose the layout into what the format the next node is expecting, right? And this optimization is tricky because we want to pick the layout so that each of the node run fast, but at the same time, we don't want to incur this additional copy or transpose operation, right? And again, you can see here that the search space is also exponential in terms of number of nodes. And it's even more because for each of the node, there are many, many more choices. So one thing that we have tried, or the first attempt is say, one way to frame this in our search is basically consider all permutation of the dimensions of each of the input and output of the tensor, right? But if we look at the search space, you can see that the search space can be extremely large. And in fact, this search space contains many invalid configurations because in reality, there are constraints between this input and output tensor in a way that not all permutation of the layout are actually valid. So this is a bad way to formulate the search space. So then we come up with a better way that make the search space more compact and only include the valid configuration. So what we do is that we say we only gonna tune the layout options for the important ops, which include convolution, matrix multiplication, also I forgot to list it here, and reshape. And then once we already assign the layout for each of these important ops, we then query for the valid, we first, for each of the important op, we query for the valid input-output layout combination from the compiler because we want to respect that constraint. And once we pick a layout for these important ops, we leverage the compiler layout algorithm, layout propagation algorithm to propagate the layout from these important nodes to other nodes in the graph. So this makes our search much more compact and only include the valid configurations in the search space. All right, the next one I want to describe is a tiling optimization. So this is the optimization at the kernel level. So once you already make decision about what ops to fuse together and they become one kernel, right? When they become one kernel, it means that when we execute that kernel, you can think of them as one nested loop. Now, if you so typically, these operations operate on the entire tensor, which can be quite big, right? And turns out that in many of the machine learning accelerator, like CPU and GPU, it have this HBM memory that is quite large, where you can fit like relatively large tensor in the HBM memory. However, HBM memory is slower to access, so the latency is not, it can be high to access the HBM. Many of these accelerators have scratchpad memory, that is much smaller than HBM, but also much faster. So one of the important optimization is tiling optimization, where we say when we operate, on a tensor, instead of always accessing the HBM memory, why don't we cache, one tile, one region of the tensor into the scratch pad, and then access from it when we do the computation, right? So we essentially like pull in one tile and processing it and like output that to HBM one tile at a time. And this proven to be extremely efficient optimization. Now, the tricky part is that it's non-trivial how to pick what is the best tile size for each of the kernel. So this is another thing that we can also tune. For this optimization, luckily the space of the tile size is usually small because it doesn't depend on the size of the graph. So most of the time we can exhaustively list all the options and then try them all. Okay, so let me go back a little bit to the search strategy, which I don't have a slide on that. But as I mentioned, for tile size, the search space is fairly small, so we can do exhaustive search. For other search problems like fusion and layout, those search spaces are much larger because operate at the program graph level, and that graphs tend to be really large. Actually, the number of nodes is exponential in terms of number of nodes, so you cannot possibly enumerate all possible choices. So for the very first version, we essentially just try simple search techniques like simulated annealing or genetic algorithm. And this is the result when we use those techniques, right? And here we essentially run the auto tuner for these optimizations one after another, and then measure the speed up from the auto tuner. Do we have any question? I hear something.
Hello, I have a question.
Yeah.
Yeah, so as you said, the tiling size is a very important parameter, but for GPU, the tiling size is pretty much fixed for a given, let's say, data type or operator. So how could this be a adjustable version? Can you give us an example about that?
Yeah, well, actually, that I don't think that's entirely true. Like in GPU, if depends on how you use the GPU, right? So I think if you use the library like Kudin, and within Kudin, and it have kind of like a manual hard code or some heuristic to figure out what is the best tile size. So it depends on the size of the input and output of that particular kernel. In the library, it have already the logic to select what is the tile size for that. And I think NVIDIA probably spent a lot of time optimizing what is the best tile size for particular input and output chip. If you write manual kernels yourself in like CUDA or like in Triton, you actually have to also pick what is the best tile size. So maybe it's hidden to the user because there's usually some of these framework also provide like what is the default option, right? But in practice, if you actually dive deep down, there are always that option that you can tweak. Does that make sense?
Okay, thank you. So, I understand your point. So, if for example, I'm developing a kernel, so I will try to derive the tile size based on the hardware configuration, like how many flops it has. So we compute the arithmetic density, something like that, right? So, if in that case, I think the tile size has a little search space here. So I'm wondering, like, if in Google there was some very complex workload, so this I would say trivial approach will not work.
Yeah, I think it depends on, like, for example, if you just developed it for like matrix multiplication, right? And it doesn't fuse with any other operation, then it's easier to come up with analytical cost model to figure out what is the best tile size. But once the kernel gets more complex, when you like fuse convolution with a bunch of other element-wise operation or additional reduce operation, or you can even, fuse like matrix multiplication, like 2 of them or 3 of them together. So when it's become more complex, then the analytical cost model is also hard to develop, right? It's possible, but you would have to put a lot of effort into developing your analytical cost model to make it accurate, right? So at that point, if you have inaccurate cost model, then that means your tile size that you pick might not be optimal anymore.
Okay, thank you. That makes sense.
Yeah. Okay, any other questions? Okay, if not, let's continue. So here is the speed up of running the various auto tuner on the top workloads that we seen at Google. So we picked about like the workloads that cover 90% of the workloads in our TPU fleet on TPU v3 for the tile size optimization and TPU v4 for the rest. And here I report the speed up average across all of these workloads. So you can see that even though for each of the optimization, we get about like 2 to 3% speed up, which is moderate, if you add everything together, right? Like if you're tuning fusion, layout, compiler flags, and tile size together, they are additive, right? So in the end, you add everything up and you get about like over 10% on average across all the workloads in our fleet. So that's a pretty significant speed up. We also use this technique to tune important production workloads that actually serve, production traffic for various Google product, and we've seen about like 5 to 25% speed up for some of these important production models. So this basic idea is shown to be extremely effective, essentially. Now I want to also tell you, right? So I've shown you so far how we can get this additional improvement over the default compiler, and it's shown to be quite effective. But how can we actually deliver this benefit to most of the workloads in our data center, right? So of course we can ask user to say, okay, let's run the auto tuner on your workload, but we put that effort into the user to actually before you run the training job or before you run your inference job, run the auto tuner. So which proved to be kind of tricky because some of the user, especially if they want to just run some experiments on their training model, they don't think about, okay, let's run the auto tuner first, right? So in our experience, we found that asking the user to run the auto tuner doesn't seem to be very effective. So then we come up with a way to, let's think about how is it possible to deploy auto tuner automatically at the scale in our data center. So, and this is the solution we came up with. We call this system AutoFDO for XLA. So AutoFDO stands for Automatic Feedback Directed Optimization. And originally, this concept had been used in like C++ compiler to basically like feed back the profile information back into the compiler to make better decision. So we kind of borrow this concept to deploy our auto-tuner. So what we do is that first we leverage a fleet-wide profiling system that we have in place at Google to basically collect and tell us what is the most important workloads in the fleet, right? Meaning that which workloads consume most number of TPU hours, right? So from the profiling information, we pick the top workloads that cover most of the fleet. And when we run the auto tuner offline on those workloads to essentially generate the best configuration within a given amount of time, and then we save that tune configuration as FDO profiles. We save that by embedding that like an embedded database inside the XLA compiler, which means that the next time when the user compile their workloads again, the XLA will first look at the database to see if there's a match, right? If it's the workloads that we have been tuned before, it's going to get a match, and then we're going to apply the best configuration safe in the database. If there's not match, then it will fall back to use the default heuristic in the compiler. So we have been deploying the tile size auto tuning using this technique for the top workloads every day, and we have been saving about 2% of total TPU consumption time using this technique. If you look at the saving versus tuning ratio, it's about 15, meaning that we spend 1 TPU to save about 15 TPU worth of time. And one thing I would like to point out is that in this auto tuner, we actually use a learned cost model that can help us reduce the tuning time and allow us to tune 20 times more kernels per day in order to cover most of the workloads in the fleet. And this is a segue to the next section where I would like to talk more about what exactly is the learned cost model and how we can use that to improve the search time. So the idea here, as I mentioned at the beginning of the talk, is that if we want to do this in a simple way, to evaluate a candidate, you can compile and run on the hardware. But this one evaluation of compilation and execution can take more than a minute. And if the graph is large, it can be tens of minutes, right? So if we can reduce the evaluation time for a single candidate, that means we can reduce the search time overall significantly. So we would like to essentially train a model that can either predict the runtime or at least ranking the configuration, right? Because in reality, we don't actually care so much about the absolute runtime. We care more about picking out what is the best configuration, right? Because when we compile a particular graph or a particular kernel, we have multiple configurations possible for that particular graph. And we want to be able to pick which configuration that will yield the fastest execution time. So essentially the goal that ultimately we want is to train a model that can rank between different configuration for a particular given program. And we have been experimenting this idea with two of the optimizations quite extensively. The first one is the layout assignment optimization at the graph level, right? So here the graph is the entire program. And then the other one is the learned cost model for loop tiling. And here is at the kernel level, where the kernel is essentially a subgraph of the operation that get fused together. So because in either of these problems, whether we work at the graph level or the kernel level, the program representation itself is a graph. So it seemed natural to use a graph neural network to model this problem. And here is the simplified version of our model architecture, where we're utilizing GNN, and we give the structure of the graph to the GNN. We also give node features as input. So in particular, we encode the opcode ID, which is basically what is the type of the node in the graph. Is it matmul, convolution, reshape, or other operation? So that get encoded in the opcode ID, which we have an embedding table lookup to turn the opcode ID into the opcode embedding. And then we encode other additional information such as input shape, output shape of the node, what is the padding configuration for that operation, or like striding or dilation. Those are in the node features, right? And we concatenate the node feature and the configuration feature that represent either the layout configuration or the tiling configuration with the node feature before we input that into the GNN. Once we feed that information to GNN, we get node embeddings, and then we can use various different reduction methods. One could be just simple reduction, where you just do mean pooling, sum pooling, or max pooling to get the graph embedding. We also try with more complex reduction methods, like, okay, let's use LSTM or transformer to turn the node embedding into graph embedding. Once we have the graph embedding, we have the final feed-forward layer that can then turn the graph embedding into the runtime prediction. Now, let's go a bit deeper into the graph neural network, right? So the concept of graph neural network is essentially, instead of, when you compute the node embedding for a single node, let's also get the information from the surrounding nodes around it, right? Instead of just encoding the node in isolation, because you get more information if you actually have the view of the structure of the subgraph around that node. So when you compute the embedding in each pass of the graph stage, or this is also actually typical for other GNN architecture, is that when you compute the embedding, you look at the embedding of yourself, but also the embedding of the nodes around that particular node. Depending on various GNN, sometimes if the number of nodes is quite large, one way to scale this is to sample. So you, instead of looking all the neighbors, some of the neighbors surrounding it, but you can also try like aggregate the information from neighbors too. Once you aggregate the information from the neighbor, we concatenate with the self embedding, and then you feed that into a regular feed forward layer and normalization layer to get the embedding. Now, if you do this multiple times, then you can see that you increase the number of hops of the neighbors that you aggregate the information for. So as we increase the number of GNN layer, the number of the neighbors each node can gather the information for is also larger. So that's GNN. Next, I also want to talk about the loss function that we use. So we can view this problem of runtime prediction as a regression problem, where we can predict that we want to predict the runtime, and we can compare that with the ground truth or the actual runtime. So a simple or a common regression loss is mean square error, right? Which I show in the first line here in this slide. But then we found out that, well, this might be hard to learn, because if you frame this as a regression task, the model have to be able to predict that the absolute runtime, right? But in our problem, as I said before, we don't actually care so much about the absolute runtime. We care more about, can we able to rank and pick out the best configuration out of the possible configuration. So we care about more the ranking. So we also try another loss function called pairwise rank loss, that essentially intuitively from this formulation, it basically count the numbers of pairs that the model can predict accurately. Whether, for example, if yi is greater than yj, we force the prediction to say that the yi prime should also be greater than yj prime. If yj prime end up being greater than yi prime, then it add to the loss value. And in terms of evaluation metrics that I'm going to show you later, the first one, we're going to report the slowdown compared to the optimal. So let's say that we are using the learn cost model to pick out the top K candidates according to the model prediction. Within that top K, if you look at its absolute runtime and pick out the best version from the top K, how does that compare to the actual best configuration in the ground truth, right? So this kind of represents the slowdown of like, okay, well, if we use the model to pick the top K, are we able to get to the optimal, right? And then the second metrics we care about is the ranking correlation. And this kind of represent the ability of the model to guide the search toward the promising part of search space. So for this one, we're using Kendalltown correlation. And the first one, let's take a look at the results for the learn cost model for tile size. Because here at the kernel level, we deal with much smaller graph, so it's easier to deal with. So let's take a look. So here is the result. The first, I want to let you focus on the first cluster of the bar chart. So this one, we essentially compare the MSE loss with the list MLE, which is one type of ranking loss. And you can see that for both validation, the score on the validation and test, when we use rank loss, the top 5 error percent, it's much lower when we use the list loss compared to MSE. So this kind of tells us that the model is able to learn more effectively when we use the ranking loss instead of the typical regression loss like MSE. Another thing I want to show you here, well, I think this is similar. Essentially, we try various different types of GNN. So we try GraphSage, we also try GCN, and the choice of the GNN doesn't seem to matter that much. Now, the next thing that seems to matter a lot is when do we combine the configuration knowledge in our model architecture. So for the early Sage and early GCN, we essentially concatenate the configuration feature, the tile size feature, with the node feature before we feed into GNN. Whereas the late Sage and late GCN, we combine the configuration feature with the graph embedding after GNN, and it's only feed into the feed forward layer. And we found that combining the configuration feature early on is extremely important. Right. Now let's take a look at a more like a harder problem for layout, learn cost model for layout configuration. And this is because we have to deal with the entire program graph, which is much, much larger than the kernel level program, right? So obviously, the first challenge we run into is that these graphs can be extremely large. The largest graph that we have seen in our production fleet is 500,000 nodes in a single graph. So this proven to be extremely difficult, especially to train the GNN, right? So one of the things we try is to, well, if the graph is big, can we partition graph into multiple segments? And then we run GNN on each of the segments independently to get the runtime prediction. And then we can sum those runtime into the final prediction. Right. Now, one thing to keep in mind is that if you do this, right, and run a regular backward pass, you will still run into the issue of you're probably going to run out of the memory on your accelerator because you have to keep the activation of all the nodes in the graph in your device. So one trick that we do is basically say, let's pick one segment to do gradient descent or the backward pass at a time. If we do this, that's mean we don't have to keep the activation of the rest of the segment, and we only need to keep the activation of one graph segment at a time. But that's mean we will only be able to do backward propagation on that one segment, so it might hurt the accuracy. Well, it turns out in our experiments that we try doing this, but it doesn't actually hurt the accuracy a lot. So it's proved to be quite a pretty simple techniques that actually make it possible to train GNN on very large graph. Another thing we have to deal with is that across different types of workload, the graph representation can be extremely diverse, right? So we might run into overfitting the graph, doesn't do very well on the test set. So one thing we try is this concept of dropout, but instead of dropping out some neurons, like the typical dropout, we say, what about if we drop some of the segments entirely, right? And then we outweigh the other active segments. And it turns out that this not only reduce the training time, it also make the model more accurate on the validation and test set. So here is the results. where the blue line is the segmented model and the green line is the segmented model with the dropout. And as you can see on the top graph, the accuracy on a training set of the dropout segmented model is not that good, but on the validation set, it's actually doing better than the segmented model itself. And here is the top K error when we use these techniques together. So the best method is the one that we apply segmentation and also the dropout together. And we compare that with if we train using the full graph methods. And you can see that this combination of the segmentation and the dropout, we actually improve the accuracy on both validation test set. So that is quite interesting. And as part of working on the learned cost model for the entire graph program, we found out that, hey, our data set is actually quite interesting and unique because it contains a lot of diverse graph and each graph is relatively big, which is quite unique compared to existing data set that people already have out there, right? So in this visualization, I show you on the x-axis the number of graphs in the data set and the y-axis is the number of nodes in the graph compared to other existing data set that we have in academic. And you can see that our data set called TPU graph is quite large in both axes in terms of number of graph and number of nodes per graph. So we thought that, hey, it would be very interesting to actually release this data set publicly so that other people and researchers can have access to this quite unique data set. So that's what we do. So we release our TPU graphs data set late last year. And as part of releasing the data set, we also run a Kaggle competition. But before we get there, let me go deeper a bit into how we collect the data. Right. So I mentioned first that the two optimization we are looking at is the layout optimization and tile optimization. Then we essentially collect graph from various types of machine learning models. The first source that we collect the graphs from is the benchmark suite that XLA used to test their compiler. We also collect the graph from different open source, for example, like TensorFlow Model Garden. So for the first source, we call this XLA source that comprise diverse types of ML models, including vision, NLP, speech, recommendation, audio. And then the second source, we name it NLP. And this source only contains graphs that are different variants of transformer models because, as you know, transformer model is extremely important, right? So we also have a dedicated collection for the NLP graphs. And the next part is that we also have to generate the configurations in order to measure its runtime. So we have two types of search space. The first one is the search space surrounding the good configuration. So first we get the default configuration from the compiler, and then we run the genetic algorithm starting from the default configuration. So for this collection, it tends to have better configuration because it's starting from an already pretty good configuration. So this is the default space. And then the random space, this one contain more diversity of configuration because it's generated from random search. So altogether, there are multiple collections depending on the source and the search space. I'm going to skip this quickly, and then we are run the competition, the Kaggle competition on this data set. This is late last year because we also want to announce the results at NeurIPS. So we have an ML for System workshop at NeurIPS that we announced the winners. And we got a really, so we got good amount of participation. There are almost 800 participants across 66 countries, and there are about 10,000 submissions. So each team can submit multiple times until the deadline. And this is my first time running Kaggle competition, and I found it to be like very good experience because to see the community engagement. So in Kaggle, there are, apart from just submitting your solution, people are also very active on like discussing and actually helping each other, right? When some people might not understand exactly how about the data format, and they are like help each other out. So there's a lot of discussion going on. People even like share their like public notebooks to other people. For example, some of the teams share, here are the statistics of the data, and they share that with other teams. So I found that to be quite refreshing to see, like even when people are competing, they're also helping each other out. And here is the result of the Kaggle competition. This one, the metric higher is better. For the tile size, we report 1 minus top 5 error. And for the layout collection, we report the Kendalltown correlation. And here I show you the result from the top 6 teams and compare to the blue bar, which is our best internal model at that point in time. And as you can see that the top 6 teams are actually doing better than our internal model back then. So not only we like get discussion and engagement from the community, we also learn really effective techniques from the top winning team as well. And here I list some of the important techniques that we learn. So as I mentioned before, in the layout optimization problem, we have to deal with very large graph, right? And it turns out that is one of the biggest challenge, right? How to make the model learn from this very large graph effectively. And it turns out that not everything in the graph are actually important. So some of the top winning teams, they shows that a simple graph pruning and compression techniques can make the model learn much more effectively. So one of the algorithm is to basically say, okay, let's focus on just the important nodes in the graph and only consider the subgraphs around it and ignore everything else, right? So this actually showed that can actually increase the model accuracy quite significantly. The other more minor tweaks that also shown to be important is that just selecting better padding value can actually help the accuracy. So I think in the data, the default padding value is 0 because that's the typical padding value. But it turns out that 0 can actually be actual meaningful feature for some of the node feature. So some of the teams say that if we change the padding value to -1, is actually make the model learn much better. Teams also try different types of encodings for the node feature. Some teams also figure out that there are some additional node feature that we can put in that also help with the accuracy. The other one that might be helping, but not as much as the other 3 techniques I mentioned, is try different model architecture. So some teams use the combination of GNN and attention model, like transformer or linformer, and they found that to also help improve the accuracy. And then, so there are a lot of things we learned from running the Kaggle competition. So first of all, crowdsourcing knowledge is extremely powerful, right? We learn a lot of new effective techniques that we have not tried before. We also found that, oh, actually not us, but some of the team found that there are some data corruption in some of the graph, and we didn't actually catch that before. But someone pointed that out. So, but luckily it was like early on during the competition, so we are able to like regenerate all the data. And one thing I would like to also share with you is that if you're interested in running a Kaggle competition on a particular data set that you have, you could also get a Kaggle grant, which is a sponsorship for you to give out the cash prizes to the winners. And this is a way to basically attract more participants. So I just kind of want to help advertise this opportunity. And yeah, I want to end a bit early so we have time for questions. And here is the reference to the data set, to the competition, and some of the papers related to the materials I talk about today. And with that, I'm happy to take more questions.
Thank you, Mangpo. Thank you for a very exciting talk. And I have several questions, but first I would like to audience to speak first. Yeah. So any questions from our audience? So you can either unmute yourself or input your questions in the chat box.
I have a question. Yeah.
Mhm.
Yeah. So in the GN work, so how many layers the model would be? Seems like it's a large number of layer in the model.
Yeah, and in fact, for our model, the model that we release as the baseline for the competition, so the one with the blue bar, with the pink bar that I showed earlier, that one don't have that many layers. So I think it's only 4 layers of GNN. And if you look at the winning solution, they also don't actually use very deep GNN. So they also, limit around like 4 to 5 layers. And I think this is also something that we learned that, even though the graph is large, the important patterns don't actually need a lot of, layers to learn. So essentially, I think that the intuition is that it's enough to actually pay attention to some, some important, like small patterns in the graph, right? So for example, we know that most of the time these graphs spend on like matrix multiplication or convolution, right? So those are the important nodes in the graph. So it seems to be sufficient to just pay attention to only the subgraph around that node, and you don't need to actually pay attention to everything in the graph. So surprisingly, it seems to us that small layers of GNN seems to be quite effective for this problem.
Okay, thank you.
I think there's also a question in the chat.
Yeah.
Okay, for evaluating parameters of compiler, how to decide when to use learn cost model or hardware for evaluation? What are the factors trade-off that needs to be considered when making decision? Yeah, definitely. That's a very good question, because as you can see that, sorry, it's now brighter. So, the learn cost model always going to have some error, right? It's not going to be as accurate as actually evaluating on the real hardware. So we have to keep that in mind. So there's definitely a trade-off, because when you use the learn cost model, it's much faster to get the feedback reward, right? But that's mean there's some amount of inaccuracy in there. But on the other hand, you can actually run on the real hardware that take much longer time, but much more accurate. So our simple solution at the moment is to say during the search, we're going to use the learn cost model, right? And then we going to pick out the top K candidate according to the model. And then we're going to use the hardware to evaluate only that top K candidate to pick out what is actually best according to the real runtime. So this is one of the simple strategy that one can do, right? But you can imagine some more sophisticated algorithm where maybe you run the learn cost model, but not until the end. You run learn cost model for a while. Between then, you pick a few points to actually evaluate on the hardware. And then you can then also learn whether, okay, is the learn cost model actually accurate for that, that graph or not? If so, then you can continue with the learn cost model. If not, you might want to fall back and say, okay, I cannot fully trust the learn cost model, and I might actually want to spend more time on the real evaluation, right? So I think they are also this sort of like more complex algorithm that learn to utilize like when I can trust the learn cost model, when I should pay more attention to the real evaluation. Yeah.
Any other questions from the audience? Okay, I think I may ask some questions. And so first, I would ask, I believe that so most of the result of the experiments is done on the TPU, right?
Mm-hmm. That's right.
Yeah.
Yes.
So I was wondering because we know that in Google's data center, you also have a lot of the GPUs. I was wondering, so how about like the generalizations of this kind of methodology when we apply to the GPU due to the underlying architecture difference, whether we need to do some kind of different strategies or the main philosophy is still the same?
Yeah. Well, we have not tried this on GPU, so I cannot say for sure whether this is going to work or not. My intuition is that I hope that the techniques should generalize to GPU as well, right? Because I think in the end it depends on like how much data you have, and I feel that if we have enough sufficient data from GPU, the model should be able to pick up and learn, the architectural difference between different hardware as well. So I think it should generalize and work on GPU, but I have not tried this, so I cannot really say. So that's one caveat there. Yeah.
Okay, thank you. And another question is diversity, right? So we have the transformer, CNN recommendation system, LSTM.
Oh, you mean like how well would it do on?
Right now, transformer gradually become the dominant area. Excuse me? Hello?
Sorry, did I freeze?
Hello, can you hear me?
I can hear you now. Yes.
Yeah. I'm not sure whether
Can you
it's my
repeat the
question or
question?
not. Okay.
Can you
Yeah.
repeat the question?
Okay. Yeah. So my question is that because we know that transformer is kind of gradually dominate the different fields, and so it's kind of we are kind of we saw some kind of convergency for the model, and also because transformer itself is kind of relatively regular, right? So it's a kind of repeated blocks, and so I was wondering, so in such scenario, whether the search space will be kind of gradually shrink down and to actually to ease your task.
Yeah, that's a very good question. And I think that that's one thing that definitely can be, the area to improve on this work. Because right now we just kind of like view the graph as, a general graph. One thing I did not mention is that the size of the graph is large because they contain a lot of repeating structure, right? So when you have, for example, transformer where you have a lot of like repeating layers, these actually get unrolled into multiple nodes in the graph, right? So you actually have a lot of repeating structure in the graph. So definitely one thing that we can take advantage of is to recognize that there are these repeating subgraph, and can we actually compress the graph, because we don't actually want to have all these repeating subgraph and make the search space really large, right? So getting off the duplication would definitely help. And then I think I'm getting kicked out from this, but yeah, so I think like essentially take advantage of that would definitely like help improve this work. But yeah, I have to go to a different meeting because someone else also waiting for this room. But yeah, thank you so much for the invitation.
Thank you so much. Thank you so much for giving the talk. Thank you.
Yeah, no problem.
Okay. Also thank everyone to join our today's seminar talk, and see you next time. Thank you, Mangpo. See you.
Bye.
Bye.